Okay, well, welcome to our March community meeting. It's been a while since we had one of these. Our last call was November 6th last year over Zoom. We've been actually pretty busy since then. I tried organizing this a little earlier, but it seemed like we were in a lot of crunch time for a while. Shortly after our last call, we were accepted as a CNCF sandbox project, so we've had a lot of kind of onboarding to do there. We released 073 and 081 in support of our product at Dell. And most recently, we've released 090. That's our first release as a CNCF project, or our first, I guess, major release. And this call we're doing through a benefit we get from the CNCF, their cloud native community groups. It's basically a white labeling of bevy.com. And we'll try to host these monthly. If you guys have comments about this platform versus Zoom, by all means, let's make sure we're using, the software that works best. But we're kind of trying out the community group software. We'll keep our calendar there, whether we use this software into the future or not. But keep those comments coming my way. I wanted to just highlight some recent community developments that I've noticed. The Pravega Akka connector is getting updated to support key value tables. ARM 64 and RISC-V support has been investigated. A contributor out of the Ukraine has opened up support issues at all upstream dependencies. He first tried getting Pravega running on RISC-V and had troubles and opened issues upstream, and then tried running the Rust client on RISC-V and open to support issues there. So I thought that was a really good effort. I got Pravega running on ARM 64, so I have a PR that upgrades all the dependencies required to do that. Documentation improvements are coming. We have new guides to help devs and admins get started with Pravega, as well as we're updating existing docs. That's maybe been a big area we've neglected. So we're kind of getting caught up there. A new website is coming soon. As a part of joining the CNCF, there's a small bit of, I guess, governance structure that they request. So we're forming a maintainers group and a steering committee. The maintainers group invites have been sent out, and the steering committee invites will be coming, and everyone's invited to join our users mailing list. Also, after this, we'll post all the slides for everyone to check out after the fact. Our next call is going to be April 16th at 7 a.m. The topic will be connectors. Hopefully, we'll overview the Akka connector, Presto, Flink, Spark, NiFi, maybe a few other things. Definitely open to suggestions, especially if you want to show your connector. And by all means, suggest topics for future monthly calls. Suggestions and feedback, please send those my way at derek.moore@dell.com. We'd like this program to be really useful for everybody and certainly highlight everybody's creativity. So by all means, let me know. Today's call, we're going to hear from Flavio about kind of the current state of Pravega. And then we're going to overview the experimental features of Pravega. So we'll hear from Shivesh on the Schema Registry, from Prajakta on consumption-based retention, from Sachin on the Simplified Long-Term Storage, from Enrico and hopefully Diego on their Simplified Long-Term Storage plugin for Bookkeeper, and then Andre on key value tables. And then wrapping up, we'll hear from Raul on overviewing his performance evaluation. Flavio, I don't know if you can share your screen. Perhaps I have to stop sharing first.
I guess that would be good. I haven't tried, so let me see what I can do on my end.
Great.
So what can you see?
I see your slides. Looks good.
Can you see presentation mode, or you see the slides, or what do you see?
Yeah, I see the full screen slides.
Okay, good. All right. Okay, so, well, first off, welcome everyone. It's great that we're having this community meeting, and I hope we have many more. And that this is just the beginning of the conversation and of a community that I expect to grow. I would like to see growing and doing more and more things. So my goal with this presentation is just to spend a few minutes talking about where we are, where we want to go with the community. I'll focus less on the technical aspects because the agenda is already pretty tech heavy, which is great. So I won't spend as much time there. I want to talk more about where we are and where we want to go from a community perspective. So that's what I'm calling the state of Pravega. I'm not sure for this crowd, most people here already know about Pravega and where it's coming from and so on. I did put one animation just so that I'm sure that everyone on the call is on the same page, at least about the context. All right, so this hopefully this is not too boring for the people who already know this, but again, this is just so that we are on the same page. So what is Pravega? Pravega is about streaming data. So the way we started this was thinking about all the potential sources of data that are continuously generating events, messages, records, whatever it is. So they can be, an end user that is doing stuff on a social network, a user that is using Uber services or Lyft services and anything along those lines. But it could also be machines. You can think of devices, sensors in IoT, or even servers emitting telemetry. So all this could be sources emitting data continuously. And we want to capture that so that applications can process that in a number of ways, right? So they might want to capture and process that data for visualization. Machine learning is very popular these days. So those are all sorts of things that you might want to do out of the data you capture from those sources. And so we did Pravega with the idea of providing a infrastructure software that is able to ingest and store data coming from all this sources of continuously generated data, and provide a few key properties: consistency, elasticity, and durability. Now, one of the key things that we wanted to do in Pravega was to be able to use scale-out storage. Main example being object store. Because it's prevalent, you find it all over the place. It's popular, it's cheap, and so it's very convenient for applications to be able to use an object store as the underlying storage for anything. And for streams wouldn't be an exception. But if we did that on scale-out storage alone, that wouldn't be very good, because streams, it has a lot to do with small writes and low latency, and doing that over an object store wouldn't work very well. So we ended up with a tiered storage, in which we have a tier that implements or that uses a durable log, and that durable log essentially serves as a way of staging data before we write it to scale out storage. Now, to write and read, we have clients, right? So we have writers and readers. So the main one that we have developed is Java, but there are the clients on the way. And so you will be able to write a Pravega or an application that uses Pravega in your favorite language sometime soon. All right, so that was a brief. That was the gist of Pravega. Now, what is Pravega used? Hopefully, I'll see more slides like this in the future. But now we'll focus on what we do. So in Dell, we have a product that is called Streaming Data Platform. And Pravega is the core piece of that platform, is the component that we use to store streams and allow applications to streaming applications to execute. So in in our history with this product, we have seen a few use cases, and I want to share just 3 examples that we have for which we have information publicly available, right? So some of the links are in this slide, and they are amusement parks, construction sites, industrial IoT. Right? So those are use cases that we have seen as part of our conversations with customers, and they have agreed to have that information out there, or they produce the content to show to discuss how they're using it. So none of these links will have a lot of technical detail on how this is used, but at least it gives us the context of some of these key use cases that we have seen. And as I mentioned, I'm looking forward to seeing more community use cases, right? I mentioned the Dell Streaming Data Platform, which is a product that we developed, but I really want to see the community doing their own use cases and talking about it, right? So in future meetings, I would really like to see more presentations about community use cases. A bit of our open source trajectory. So we open sourced in 2017. Right, so we opened the code in 2017. Our first open source release was on December 2017. As you can tell, it was pretty close to Christmas, to the Christmas break, to the end of the year break. So we pressed hard to get it out. And after that, we had a number of other major releases. So we just released 090. So it's fresh out of the oven, was released a few days ago. And as Derek mentioned, in 2020, after we spent a few years maturing, stabilizing, evaluating performance, doing all sort of things on Pravega, we decided it was time to propose it to an organization that was vendor neutral and that could host Pravega as an open source project, so that we could build a community that, again, is vendor neutral. And so we proposed to CNCF. CNCF accepted our proposal, and we are now, we just started sandboxing. So there is a transition going on. We're doing all sort of things, overall bootstrapping for, say, communication channels, email lists, and we're using that opportunity to also revamp the website. I think Derek also mentioned that, so you should see a brand new website sometime soon. Doing some organization of repositories. And one key thing that I believe is very, very important for us to build a healthy community, which is to document our governance model. I mean, right now, so CNCF doesn't impose one on us. They have, of course, guidelines and then suggestions and so on, but they do not impose one on the project. But we need to do that, because otherwise we cannot do simple things like deciding when it's time for a contributor to become a committer. So we need to document all that so that there is transparency on how we do things, and that the community outside Dell can participate. So that's a very important goal for us for the near future. And if you're interested in the tasks related to the transition, there is the GitHub issue that I put as a reference on the at the bottom of the page. So Derek has been the main person working on that, and there is a laundry list of things that we need to get done. One interesting thing for me with respect to repositories for the project is that all projects that participated in the past had one single repository, and now we have an org, and CNCF allows that. It has no problem with it at all. And so we have a Pravega org, and we have right now a total of 43 repositories for various things, right? So we have, of course, Pravega Core, which is the stream store engine. But then we have a number of repositories for connectors, for Kubernetes operators. We have a Pravega operator, a bookkeeper operator, a zookeeper operator. We have client bindings. We have all sort of tools, Pravega tools for Flink, benchmark. So there are 43 repositories total. I'm clearly not listing them all here, but I encourage everyone who is interested to go look at them and see what is available. So in the end, it's not about Pravega, the stream store engine alone. It's about the ecosystem that we can build so that we can support all types of streaming data applications. So that's one reason for having a lot of these repositories, which is, again, to build an ecosystem around the stream store engine. As for contributions, so the number of unique collaborators that I could get out of Git is 135. The vast majority of that is from Dell. I don't know exactly what number that is. I didn't look into precisely what's coming from Dell and what's not, but clearly the vast majority is coming from Dell at this point. And I do want to see more non-Dell contributions, not only for the Pravega stream store engine, but for everything around Pravega for the whole ecosystem. So if you're interested in contributing, if you want to contribute but you're not sure how to do it, look for guidance, maybe a mentor in the team. Like reach out on Slack, for example, and I'm sure that someone will volunteer to help you out. The whole team is very eager to work with the open source community. So if you're interested, please get involved. Going forward, we expect to see, of course, more Pravega features. We haven't stopped on the feature set we have right now. We'll be doing more and more things, for sure. But one important focus area for us right now is the ecosystem. Improve our connectors, build more connectors, build all the necessary infrastructure so that we can do a better job at building streaming data pipelines. So if you're interested, again, get involved. One very nice link to start with, if you haven't checked, is our contributions guideline. So that tells you everything from how we create a pull request to how we should do a description, code style, and all that. So have a look and reach out if you need any help. Now, last thing is I will be shipping T-shirts for the best questions. So I want to see who is really paying attention and asking hard questions. Hopefully, you save your hard questions to others, and you won't ask hard questions to me. And so when you ask hard questions to others, you'll be entitled to a T-shirt. So for the best questions, I'll be reaching out to you after the session, and I'll get your address and ship a T-shirt to you. All right, and that's it. Thank you. Hope you enjoy the rest of the sessions.
Okay, great. Shivesh, I guess you're up with.
Sure. Thank you, Flavio. That was fantastic. I'll share my screen now.
Can I start with the first good question? Can we get the Pravega T-shirts?
No. Is the problem is that there are no. Okay, I think I have an extra T-shirt, which I have not used, by the way. It's not mine. I have never, I haven't even tried it, but it is XL. It's an XL shirt, so it's too. I don't know. I would guess it's too large for you, Enrico. But you tell me. If you still want it, you can have it. As far as I can tell.
Good.
All right. Hi. So can you guys see my screen?
I can now, yeah. The full screen.
All right.
The full slides.
You see the PowerPoint presentation, right? Earlier, I think I shared my browser, so I was going through that whole infinity thing. Yeah. All right. So hi, I'm Shivesh. Most of you over here may know me, but those who don't, I've been with Pravega almost from the start. And last year we built Schema Registry, and we recently did an O2 release for it along with Pravega 09. So today we'll cover Schema Registry. Right now it's still in the experimental phase. So the API sets, although they are stable, but they could potentially change based on the user feedback and anything that we get. And that's why we are still in the experimental beta phase for Schema Registry. So to start with Schema Registry, the motivation for us building the Schema Registry is essentially Pravega is an unstructured storage. It doesn't impose any structure on the data. It receives raw bytes, it ingests raw bytes, and delivers raw bytes back to the application reader, right? So the writers, they serialize the raw bytes, and the readers deserialize it. They need to know the structure of the data that has been written to make sense of it. This works well for most applications where you actually have baked in this structure or the schema of the data that's going in, and you know how to make sense of it. But there could be applications like you want to do any business intelligence on your data, you want to run queries on your data that's there in your Pravega stream. And that can be enabled only if you have some access to the structure of the data that's there in Pravega. And that's where schema registry comes in. I mean, you could have included the schema along with the data as you were writing it into the stream, but many a times your schema itself could be pretty bulky, and it could be bigger than the actual payload size. So it would be a lot of wastage space, and you would be doing this for each and every event that you write, which effectively means a lot of space wasted. So what we have done is something which is also done with other schema registries. We create a separate service in the Pravega ecosystem called Schema Registry, where we actually store the schema for the data that you have in Pravega, and we allow you to tag your data with the schema registry issued identifiers for the schema that you have, so that at the read time, when you read this data, you can actually resolve it by querying the registry service and get the corresponding schema for the ID that you have. So schema registry provides you the schema for the data that's there in Pravega. It's not just limited to that. It also helps you manage the schema that you have in Pravega. And by schema management, you typically imagine a scenario where you are actually working with some problem where you've created or defined a schema, a structure for your data, which has, say, n fields. And subsequently, as your business needs change, few months or years down the line, you want to modify this structure to incorporate the new business requirements. So you have additional fields that you want to include over there, right? That's called schema evolution. You are evolving your schema from whatever earlier state it was into a newer state. And you could have certain in data that's being ingested with potentially newer schema, whereas you may not have chosen to upgrade all your writers, and some writers could be ingesting data with older versions of the schema. So this could lead to compatibility situations if your reader applications are not expecting changes to the schema. So it depends on the context in which you are running your application, in how you are going to be making use of data in Pravega. But schema registry allows you to manage the schema and evolve the schema with respect to the compatibility policy that you want to choose for your data in Pravega. So for example, if you want backward compatibility, by backward compatibility, logically the way to think about it is you've got the reader, which can be thought of, if I have to draw the analogy, think of it as the server client model, where the Pravega reader is the server and Pravega writer is the client. The writer is initiating a request, and the reader is supposed to make sense of it, consume that data, right? So here backward compatibility means your server should be able to read data or requests coming in from both latest client as well as older client. So in this example, in this analogy, it would be readers being able to read data written by both older writers and newer writers. Similarly, if you invert this, the forward compatibility is when your server is on lower version and your clients could potentially be on server's version or higher version, where your writers are on higher version and your readers are reading with a schema which is of lower version. If your application is deployed in such a scenario and you want forward compatibility as your compatibility policy choice, you would configure that. And what schema registry does here for you is, it as you are evolving your schema, as you are changing your schema, you bring the new evolved version and register it with the service. The service validates this new schema and only accepts it if and only if the policy that you have configured actually this new schema satisfies that policy. If it does, then that schema is accepted, and then you can subsequently use that schema in your Pravega applications. So compatibility is very context specific. It's your application's usage and how you are deploying and upgrading your application. Schema registry helps you manage and enforce that compatibility policy, apart from being a serving layer for the schema that you have in your application. So the way we have actually built schema registry is, we have decoupled it completely from Pravega. We have conceived it as a separate service, and this service has its own data model. It does not, it has analogous concepts to Pravega's data model. It has an analogous concept to a scope and a stream, but it has its own way of organizing these schemas into something called schema groups. Schema groups are logically equivalent to a Pravega stream, and the typical use case pattern is that for each Pravega stream, you would create a schema group, and there you would store and manage and evolve the schemas for all the data that you would be writing into that Pravega stream. But the important point to note here is schema registry is actually completely decoupled. It could be used in use cases outside of Pravega. It's not tied to Pravega streams concepts in any way. And secondly, you could use Pravega without actually having to use schemas. You could continue using Pravega the way you've been using it, and nothing prevents you from doing that. So that's a high level overview of schema registry. So as I mentioned, we've got this concept of a schema group, which is essentially the logical collection that's offered by the service. And this is a named artifact under which you actually store all your schemas and evolve them. So for example, if you've got a schema group called group 1, where you want to store schemas of type user, and the serialization format that you've used is Avro. So you've defined your schema in Avro format, and you've specified whatever compatibility policy. We've got a choice of different compatibility policies to choose from, ranging from backward and forward policies to backward transitive, which means compare with all the previous schemas. Backward till, compare with all the schemas till a specific version. Similarly, forward and forward till, and bidirectional, which is called full, and full transitive. So that's how things stand. And what schema registry does is it stores a version history of your schemas. It allows evolution of this schema based on the policy that you've chosen, and it assigns unique identifiers to schemas so that you can actually tag your data with this schema identifier, and the readers can actually resolve the schema corresponding to that data by talking to schema registry. So this is the high level concept, and this is a 20,000 feet view of schema registry architecture. It's actually you would typically deploy it in a high availability mode with more than one instance running. Each service instance is actually stateless. It caches these schemas, but it durably stores schemas in Pravega. Pravega has key value tables that Andre will introduce to us later in the day. So we make use of key value tables to store schemas for each group. So all the metadata related to a schema group is actually stored in a dedicated table for that schema group in Pravega tables. And we provide a client SDK that Pravega applications can actually make use of. This schema registry client SDK, along with schema registry serializers SDK, actually abstracts away all the interaction that you have to do with schema registry, and you write your Pravega application the way you write it right now. I'm assuming people are familiar with that, or at least I'll take that leap of faith here to assume that everyone is familiar of how to write Pravega applications with Pravega Writer instantiation and Pravega Reader instantiation. So the way you plug in schema registry there is Pravega applications provide a serializer interface. Basically, let me get to that in a bit. Basically, Pravega applications provide a serializer interface, and schema registry provides implementation of this serializer interface. So when you actually instantiate a Pravega writer, what you do is you instantiate it with a particular serializer that this writer library then makes use of to receive each of your data and pass it to this serializer, which would serialize it and give the raw bytes to the Pravega client library, and Pravega client library then transmits these raw bytes over to the Pravega data broker segment store, right? So this is where we actually inject our schema registry. We provide serializers. We have serializers for Avro, Protobuf, and JSON. Apart from that, we allow custom serializers that you can define and use. And for Avro, Protobuf, and JSON, we have got this good decoration of extracting or getting the schema from either the generated classes or the POJOs if that serialization format allows for it. For example, Avro and JSON. You can take a Java POJO object and extract a schema out of it. So all you have to do is just say JSON schema dot of your class name or Avro schema of class name, and it will get the schema which will get registered with the service. So in a Pravega application, this is how it would essentially get used. You've got your event writer where the schema registry serializer is injected, and when you write data, what it will do is it will first query schema registry, and for a writer this happens first time when you have instantiated the serializer. It talks to schema registry, it says this is the schema that this writer application wants to make use of. Schema registry provides the identifier that uniquely identifies that schema. Then you tag your data with that identifier, and that data is written into Pravega, and at the read time, when the reader reads those bits, it knows that the first few bits are actually the schema registry issued identifier, so it resolves it against schema registry, and it makes use of it to deserialize the data from that point on. So different events in Pravega stream could be tagged with different IDs because they would have been written with a different schema potentially, and readers could resolve that, and while reading they actually cache the schema that they've seen, so that every time they see an identifier and they've already retrieved it from the registry service, they don't have to make a network call to get the schema again. So they optimize it by caching the schemas that they've already retrieved and work with that. One other interesting thing that we have done is we've gone over and beyond just the schema. What we also allow you to actually get unique identifiers for is a concept called encoding ID. This encoding ID essentially represents your schema as well as any additional encoding that you want to do on that serialized blob. So for example, if you are serializing it and then compressing it, and let's say you've used snappy compression, so you could tag the fact that this data has been encoded as schema plus snappy codec which has been used to compress it, right? So we allow you to register this fact with the schema registry that this data has been encoded in this specific way, and we issue a unique identifier for a schema plus codec pair. So a codec is just a string name identifying what encoding you've used, and it will typically be the MIME type names. And if there are additional property sets that you want to associate with it, you could do that. And the registry issues an encoding ID for a schema plus codec pair, and this is encoded along with the data. So we've got 1 byte reserved as the magic byte for our schema registries encoding format, and then we've got 4 byte which is to encode the identifier. So each data that's being written into Pravega using our serializers actually has these 5 additional bytes. So that's the additional cost that you actually incur while using schema registry. For writers, as I said, at the time of instantiation of the serializer, they just register it with the service and get the identifier corresponding to the schema that serializer is going to be making use of. And from that point on, it doesn't really need to interact with the registry service. And a reader application needs to interact with the registry service for each unique encoding ID that it sees. And once it has actually retrieved the information corresponding to that encoding ID and cached it, it doesn't need to contact the registry service again. So there is no latency impact as such, except every unique time you see a new encoding ID. But there is some payload size cost, which is about 5 bytes per event. And schema registry is typically more meaningful and useful if you have some structure to the data, which is relatively big, right? If you're just writing integers into the stream, which are going to take 4 bytes, and you are encoding it with additional 5 bytes, that does not really make a lot of schema registry for you. This is
we might have lost a few seconds of audio. So what was the last thing you heard? It was just like maybe 10 or 15 seconds.
Okay, so I'll just continue on. This is how you instantiate your writers, as I've shown earlier, and similarly you've got your readers. You could actually deserialize this data into a specific schema, or you could deserialize it into a generic so for example, Avro has generic record, Protobuf has dynamic message, JSON will just give you a linked hash map, right? So you could actually deserialize into that generic format as well, and that's useful in the BI applications where you want to know the structure, but you don't want to write specific code or include that generated class in your package and compile it, right? So in those cases where you want generic deserialization, we have the generic deserializer versions available as well. In this slide deck, I'm just showing the specific deserializers where you are deserializing it into the test1 class that you have, and all the events will actually be deserialized into that schema. So yeah, that's about it. I don't know if I've exceeded my time or I've been within the time. So we'll open for questions now.
You said you said schema management's built in. Does that mean, I guess there's content type awareness inside of Schema Registry?
So you declare that this is my content type. So my schema is of type Avro format, or my schema is in JSON format. And then Schema Registry has compatibility checkers built in. So presently in the current release, we have the compatibility checks only available for Avro, but we have work in progress for JSON and Protobuf compatibility checkers, and we plan to make the whole compatibility checker logic pluggable. So essentially, you could plug in your own custom formats compatibility checks and do your own management, and Schema Registry will expose an interface that you have to build, that you have to implement and plug your management story in. But it is content aware in the sense that it needs to know which format you are writing your schema in, if you want to do these management specific activities like enforcement of compatibility policies. So Schema Registry, as I said, also allows you to store schema in any of the other formats as well. You declare that this is your format name and you're storing the schema corresponding to that format, but then it's an opaque blob for us that we store. We don't know how to parse it or make sense of it or enforce any policies on it. And eventually when we make the policy check pluggable, people could inject their policy checkers, and they could make sense of what that schema looks like, and whether it's compatible with the earlier versions or not. Does that answer your question, or was it?
Yeah, that's informative. No, that was exactly what I was looking for, I guess.
So I had a question about schema groups. So schema groups seem to be something similar to scopes for streams, right?
So I have to apologize. Shivesh, you had some echo, and so I muted you while Prajakta was asking. But apparently I can only mute you. I cannot unmute you. I don't know. This is kind of bizarre. You have to unmute yourself. Sorry.
Okay. So yeah, schema groups are analogous to a Pravega stream. Schema groups is where you store your schema that are related in nature, and the way we use it in Pravega applications is for a stream you would store all the related schemas in a schema group and evolve them. So even for scenarios like event sourcing or message bus, where you have multiple types of events being written into the same Pravega stream, you could actually, so Schema Registry allows you to have multiple types of events within the same schema group, and you could evolve each of them independently. It also allows you to have same schema type in different formats. So for example, if you have the same schema definition in Avro and JSON and you want to store that in schema registry. So let's say your user, your schema type was user. You were trying to define a structure for your user object in both Avro and protobuf and JSON because your different writer applications were written to use different serialization formats, for example. You could do that. You could store these different formats within the same schema group and evolve them independently, where schema registry would perform compatibility checks for each of these schemas with the same type and same serialization format schemas that have been stored under this group, and enforce your policy and accept and evolve the schema subsequently. And the concept analogous to a Pravega scope is something called a namespace that we have. So namespace is nothing but a named entity where all the schema groups have to have a unique name. So if you have so just like your scope, a namespace is your organizational abstraction that we have there.
Got it.
So where have we? Yeah, you go, Ro.
Okay, it was just a question. I mean, Shivesh, you mentioned that that Schema Registry is completely decoupled from Pravega, so it can be used as a separate service. But then in the next slide, you showed dependency, with Pravega key value tables to store the data, right? So, I mean, how do you explain this? I mean, this is Pravega key value tables, but could be any other key value store, and this could be the reason for that?
So yes, we have abstracted out the storage layer in our schema registry implementation. So potentially we could have a database or any other NoSQL key value store that we could use instead of Pravega tables. But typically schema registry would be used in the Pravega ecosystem.
Yeah, sure.
So you would deploy schema registry, and we need some durability and consistency guarantees for the schemas that we are storing, right? And we've already got a storage system that provides all those guarantees in Pravega. So we make use of that to store our schema in Pravega itself.
Yeah, good. I mean, the only thing is that you said that it was not independent, and then there was Pravega, so it could be Pravega any other storage system that could meet the same semantics, right?
So theoretically, it could be anything. It's just that we only have the Pravega table-based implementation as of now.
Perfect.
And the decoupling that I spoke of is primarily if you think of the storage abstractions that it provides in terms of it provides your schema management as schema groups, right? And Pravega provides a Pravega stream as the storage abstraction where you're storing your data. These two concepts are completely decoupled. It's just that as a logical relationship, you establish it in your application and you say that for this stream, I create a schema group where I store all its schemas.
Okay.
So conceptually, you could actually use that same schema group across multiple streams if they were using the same set of schemas. So if you had a data pipeline where you had multiple streams, you could create one schema group where you are evolving these schemas, and in your application, each of these applications could be configured to use that same group ID.
Yeah, got it. Thank you.
Flavio, you had something as well?
No, no. Yeah, we can go ahead. We should go ahead. Otherwise, we will run out of time.
Yeah, we might move on to Prajakta. Prajakta's going to talk about consumption-based retention, which is a really cool feature, I think. Yeah, thanks for that overview of Schema Registry, Shivesh. I think there's a lot to our Schema Registry that's different from the others that are out there, especially with respect to that evolution stuff. Okay, I can see your slides, Prajakta.
Okay, cool. So hi everyone, I'm Prajakta. I've been with Dell and on Pravega for the past 2 years. And today I'll be talking about consumption-based retention, which is an experimental feature in 0.9. And this feature primarily deals with how Pravega handles retention for its streams. So before we jump into consumption-based retention, I'd like to give an overview of how data retention is done for Pravega streams today. So a stream can be configured to have no retention policy at all, which essentially means data is never auto-truncated, but of course manual truncation is possible. Or it could have a size or time-based retention policy. What this means is in the retention policy, users could specify a min limit beyond which if the stream specify a min limit so that it's an at least limit. And so if the stream grows, at least as much data would be retained as is required by the size and time limit. So truncation for data retention is done at periodic intervals at every retention cycle. It's done by the controller. So every time the retention cycle runs, a new stream cut is generated at the tail of the stream, and a truncation can happen only at a specific stream cut. So when a stream is found to have more data than the configured retention limit, it is truncated at a stream cut such that it satisfies the policy. So let's look at a Pravega stream with these segments running from S1 to S12, and the orange dotted lines represent stream cuts taken at periodic intervals. So assuming we have a tail stream cut SC6 and the size-based retention limit is set to 30 gigs. So what we would do is we would calculate the size of the stream starting from the tail stream cut to every earlier stream cut. And at that particular stream cut where our min size is satisfied, we would choose to truncate the stream. So in this particular example, at SC1, the size of the stream is about 100 gigs, which means between SC1 and SC6, the volume of data is 100 gigs. SC2, we have 80, SC3, we have 65, and SC4, we have 50 gigs. At SC5, we have 25 gigs, but this cannot be chosen because we need to maintain at least 30 gigs of data in the stream. So we choose SC4 as the truncation point. So this is broadly how data truncation happens in the stream. There are a few limitations of this approach, and one of those is that stream truncation is completely agnostic of reads of the data by reader groups. So unread data could be lost, and in certain environments where the storage space is limited and streams tend to consume a lot more space with this approach of data retention, there is no max limit on stream size. So for environments like edge environments, this can actually be problematic. So that brings us to why CBR or consumption-based retention. Some streaming use cases don't require data to be stored over the long term, and once data is read by specific reader groups, it can be deleted. Certain environments like edge gateways could have constraints on storage capacity, so we need to move data out as soon as it is read. And so this is precisely where a consumption-based retention policy helps. So what exactly is CBR or consumption-based retention in Pravega? So CBR provides that a stream truncation can happen based on read positions of specific reader groups reading from the stream. These reader groups need to be created as subscriber reader groups. Read positions of non-subscriber reader groups do not impact stream truncation. And the stream retention policy also has a max limit in addition to the earlier min limit that was discussed. What the max limit here means is it's an at most limit beyond which we wouldn't want the stream to grow. So how does one configure a consumption-based retention policy on a Pravega stream? So the existing retention policy for a stream can stay as is. To enable CBR, what we need to do is update the reader group's configuration on client to be a subscriber reader group. If all reader groups for a stream are non-subscribers, essentially that means there is no consumption-based retention, and the earlier retention policy that was in force would continue to be used. Optionally, we could also set a max value, which is an at most limit on the stream retention. This defaults to long max if it is not set. So a subscriber reader group with CBR periodically publishes a stream cut corresponding to its read positions in the stream to controller. This stream cut is stored on controller, and when the retention cycle runs, stream cuts from all such subscriber reader groups are used to compute a single subscriber lower bound stream cut. This subscriber lower bound stream cut is essentially a stream cut that makes sure we don't lose unread data from even a single subscribing reader group. So, which is why it's called a lower bound. The stream is truncated at this subscriber lower bound stream cut subject to the min-max limits that are set on the stream retention policy. Essentially, what that means is if the subscriber lower bound is between the min and the max satisfying stream cuts, then we choose to truncate the stream at the subscriber lower bound. If the subscriber lower bound is less than min, which means truncating at the subscriber lower bound will leave less data in the stream than the min required, then we choose to truncate at min. If subscriber lower bound is greater than max, then we choose to truncate at max. So as I had mentioned earlier, to trigger or to enable consumption-based retention, the only change that is needed is on the reader group configuration. There is no change needed on the retention policy for the stream. And there's a retention type parameter that has been added in the recent release, which can have 3 possible values. The first one, automatic release at last checkpoint, is selecting this option basically makes sure that a subscriber reader group automatically emits a stream cut corresponding to the last checkpoint as a read acknowledgement to controller. So to say that it's safe to truncate the stream at this point because I have completed reading up to this point. The other option is manual release at user stream cut. So if the user chooses this option, what it means is the user has to generate a manual checkpoint and publish a stream cut corresponding to this checkpoint using the update retention stream cut API. And there won't be any automatic publishing of stream cuts from client to controller. If the user chooses the third option, which is also the default, it essentially means there is going to be no consumption-based retention for this particular reader group, and its read positions do not impact stream truncation. Yeah, so that's all from me. Any questions?
Are there other systems that have a similar, I guess, subscription truncation or?
Well, I have not
have
found this feature in any other streaming systems, at least.
Individual message acknowledgement might be.
Yeah, they do have message acknowledgement, but what this does is based on the acknowledgement, it's doing deletion of data in the stream.
So a quick question. In one of your slides, you talked about max and lower stream bound, like lower
min
limit,
and max,
right?
that's right.
Yeah. So what happens when the max is lower than the stream? What is the right term there? Stream cut, lower bound.
Lower
right?
Bound. Yeah, subscriber lower bound.
Subscriber lower. Sorry about that. Yeah. So subscriber lower bound is greater than max. What happens, and does that mean we lose data?
Yes, that does mean we lose data because essentially the user has configured the stream such that we never want to maintain more than as much amount of data.
Yeah, understood. No, I just wanted to confirm that. My
Yes,
understanding was correct.
That's how it will be.
Okay.
Any final questions, or shall we move on to the next? Let's see.
Sure.
section on simplified long-term storage.
So let me share my screen. And you will see that inception thing for a while, but yeah. Okay. So my name is Sachin Joshi. I've been with Dell for a little bit more than 2 years. We are going to talk about SLTS today, which is introducing simplified long-term storage. My aim for this talk is to set the context, explain the big picture, explain the motivation behind why we are doing SLTS, and then go into enough details so that you can start exploring it. So why LTS? So Pravega is a streaming storage, and I have underlined storage because that's the most important word for me. It's not just a messaging system, it's a storage system. And what that means is durability is fundamental. Once we acknowledge the data is never lost. Also important is that performance is critical. Flavio earlier explained that we want to have a system where we can ingest data and read the data at low latency, and at the same time, it provides high throughput. Storage efficiency is also important. We do not want to have storage overhead, duplication of data. We want to have a single unified API that works for real-time data, historical data. So it's an excellent choice for Kappa architecture. The fundamental tenet of Pravega is the steering, Flavio talked about it earlier, is automatic, which means that the tiering is done automatically between low latency short-term storage and large capacity external long-term storage. It's going to be space efficient, it's going to be performant, and most importantly, it's going to be completely transparent. The last point which distinguishes Pravega from others is Pravega works with your own external storage. It could be cloud native storage, it could be multi-cloud solution, it could be a specific cloud solution. And we want to meet customers where they are already moving, and those are object stores. It also enables age. What Pravega does is it actually converts your choice of external storage into a storage that Pravega can consume, store, and utilize. Like I said, LTS, that is a long-term storage, is integral part of Pravega storage. Traditionally, we used to do what was called Lambda architecture. The events were ingested in two separate systems. There was a speed layer, there was a batch layer, there was a duplication of effort and whatnot. The right way, or I would say Pravega way, is you ingest the data once and you have a streaming platform which allows us to read real-time streaming data as well as it serves the data for batch. Again, LTS is integral part of Pravega storage. Traditionally, what we used to do was we used to have lots of applications that have lots of their own way of storing data, and that data was never shared. The Pravega way of doing things is you have a single storage system where all of your data can be stored in a single place. And with the use of Pravega middleware, you can utilize that data. You can use that data in multiple applications. So quick background, the fundamental concept in Pravega is stream. And for this particular talk, the most important concept is the streams are made up of segments. So if you look at the diagram on the right, at the top, we have a stream, which is composed of multiple segments. As the stream progresses, as the time progresses, we might actually add more segments, or we may actually merge multiple segments. The fundamental thing to remember here is stream is composed of segments. And the segments are, the best way to think about segments are just a stream of bytes. And Segments can be added at the end, added to at the end, and they can be truncated at the front. Segment store, and I think that the diagram is a little smaller than what I expected, but below there is like a very high level, like 20,000 feet diagram of how the general architecture looks like. So the Pravega client talks with controller and segment store, which are both stateless services. They depend on stateful services, which are Zookeeper for configuration information, Bookkeeper for write-ahead log, and perhaps Cache for the local storage. Then these two things they depend on tier 1 storage, and the segment store automatically tiers data between tier 1 storage and tier 2 storage. And by tier 2 storage, we mean your external long-term storage. It could be object, it could be file system, it could be your own block storage. These are the storages that segment store will be able to utilize. So the assumption here is the tier 1 writes are asynchronous. So client actually doesn't directly write to the tier 2. The tier 1 is where the data is ingested, and like Flavio said, the data is staged until it is moved to tier 2. The segment is opaque sequence of bytes. As far as segment store is concerned, we do not actually interpret any of the bytes inside a segment. So with this background, here is the goal. Here is the purpose why we need SLTS. The goal of SLTS is to provide segment abstraction to the upper layers. Like I said, segments are dynamic. They grow at the end, so we keep on appending the data, and they shrink at the head end, so we keep on truncating them at the head end. But otherwise, once written, that sequence of byte is immutable. Segments are the foundational building blocks of everything Pravega. Segments are used everywhere in Pravega. The user streams, the attribute segments, the key value tables, internal Pravega streams, even client state management, and a lot of other things that the Pravega is built on. They use segments to store those data. And all of these upper layers actually assume that the segment abstraction works as expected. And the abstraction is pretty simple. It's a sequence of bytes. You append at the end and truncate at the front. So what are the challenges? One of the biggest challenge with object stores is how do you actually build such a dynamic entity like a segment with immutable objects? So that's one challenge that SLTS needs to solve. The second challenge it needs to solve is how to enforce single writer pattern. When in a distributed system, you always have a partition, you always have a possibility of zombie servers and split brain scenarios. And so how do you actually strongly enforce the single writer pattern? The third challenge is how do you actually implement atomic appends? One of the things that we have to deal when we are dealing with object stores is how do you deal with eventual consistency? And the last problem, which Prajakta briefly talked about, is during the retention cycle, we have to decide whether to truncate a segment or not, and how do you actually achieve that at the low level. So I'll quickly skip through these problems, and then we'll come back to like what SLTS is, how it solves those problems, and so on and so forth. But let's first quickly go through a couple of problems. So the problem number one is split brain and fencing. The requirement is data is appended atomically, and we have a strong writer pattern, strong single writer pattern. The split brain is any time when we have a partition and two servers legitimately think that they are the owner of given segment and try to write it at the same time. So to avoid data corruption and basically writing garbage, we need to solve that problem. And this can happen because first of all, it's a distributed system, but also because of long GC pauses, right? NFS locks are not NFS locks are problematic. The HDFS appends are atomic, but they are not concurrency safe. The two servers can write and append the same blocks again, and it will actually happily accept those two requests and append duplicate data. AWS has a bigger problem. AWS S3 has eventual consistency. And the current solution, the current implementation actually requires individual providers. Individual providers, by that I mean NFS provider or S3 provider or HDFS provider to solve that problem. So they might actually use some fencing logic, which becomes very complicated because each and every provider has to implement the logic for fencing and handling split brain scenarios based on what their primitives are. And so essentially, instead of solving that problem in one place, we are kind of distributing that problem, and each and every provider has to solve that problem again and again and again. So that's a downside. And it just makes life complicated for people who are implementing those storage providers. The second problem, and I think this is a subtle problem, but a very important one. These days, for the right reason, the object stores are very popular. But for streaming service like Pravega, they come with a problem. And the problem is the objects are supposed to be immutable. And what that means is once written, that same object cannot be modified. You cannot append to that object. You cannot modify a certain range in that object. If you want to modify that object, you have to replace the whole object. So if think about appending data to segments, what that means is we have to read the data, append that data locally, and write that data back. But then we still have to deal with other problems where now we have to deal with eventual consistency. The reader, or when you read back that data, are you going to get the older version or a newer version? And so object store actually have this very interesting problem where you are not able to modify the existing objects. And so what that means is we have to find a solution where we have to simulate, or we have to create that abstraction of a nice segment that can be truncated at the front and appended at the end using these immutable objects. So I won't go into all the other challenges. I think those are kind of we'll touch base, but these are the two challenges that SLTS definitely has higher priority. It's a higher priority challenges that SLTS must solve to move forward. So we are kind of defining the scope of SLTS. SLTS again means simplified long-term storage. And the reason for using that simplified word is the first problem, which is until now, we were kind of expecting each and every storage provider to solve the fencing problem, to solve the zombie problem, how to kind of strongly enforce the single writer pattern. In SLTS, our aim is to simplify the API contract for the storage bindings. We eliminate need for complex fencing during failover and give the freedom to optimize append logic, leverage the storage native merge and concatenation capabilities. SLTS also aspires to provide extensions point for the future, like additional background services like defragmentation, integrity checks, possibility of data compression, encryption, erasure encoding, and all those sort of things. We also can support access control, multiple tiers. Again, that's not what we are doing in this particular 0.9 or 0.10 milestone, but it's an extension point for the future. What is out of scope for SLTS? We are still requiring Pravega to read data from Pravega. We are not talking about exporting and importing pre-existing data in other formats. For example, Avro, multiple tiers, at least for short term, it's out of scope. So with that background, let me quickly go into so we talked about what SLTS is trying to solve. Now we are going to deal a little bit about, talk a little bit about like how SLTS solves that problem. On the left, you have segment store current architecture, and the right, we have a new design. So as you can see, there is a cache, and that cache actually calls two components called storage reader and storage writer. The older storage system was called async storage. It actually called into something called rolling storage. And then finally, at the bottom layer, there was these things called sync storages, which is either HDFS, NFS, or extended S3. With SLTS, what we are doing is two things. First of all, we are introducing a metadata table store, which stores the data about chunks. It stores the data about storage layout. And we are also introducing storage optimizer services, which are garbage collection, defragmentation. The main change is the chunk store, the async storage is replaced by chunked segment storage, which talks with metadata, the table store, and which talks with chunk storages. The chunk storages are the new API that we are exposing so that, and I will talk about that in a minute, so that they can actually, the storage providers can implement a simplified API. So the chunks segment storage is the component that manages the underlying storage and talks to the storage providers using chunk storage API. So in short, what SLTS is a unified chunk management layer. So what is segment? What is chunk? Chunk is a unit of storage. You can think of it as a chunk as an actual thing that gets stored on your external tier 2 storage. If it's a file, then if it is a file NFS-like storage, then it's a file. If it's an object storage, then it's an object. So it's the leaf node in the storage hierarchy, and it's a unit of storage. It can support append, but the only expectation we have is if it supports append, the only requirement is that it has to support append-only writes. Right? Sorry, the right way to say it, as long as it supports append-only writes, we are able to utilize your storage. The unified chunk management layer enforces a strong single writer pattern with this particular assumption that is enforced everywhere, is the chunks can only be written by the instance that created them. That eliminates the problem of two different server instances trying to modify the same underlying file or object. So that's one of the tenets of the design. The second is immutable. The chunks are immutable. Once they become inactive, they're considered sealed. They will not be modified. The chunk names themselves are arbitrary, but the only requirement is that they must be globally unique. Like I explained before, the segment is made from multiple chunks. You can think conceptually. There is a diagram at the right bottom. You can think of it as a segment is segment is made up of two types of records. A segment header has information about segment itself, and then individual chunks, you can think of them as metadata records that point to the underlying files or objects. And conceptually, you can think of a segment as a linked list of chunks. A new chunk is added whenever a new segment is written for the first time, obviously. After failover, I just explained that we enforce this strong single writer pattern. Or the underlying file or object reaches its limit. And the fourth is when underlying storage does not provide safe append semantics. And so in case of failures, we might actually decide that it's more safe to actually start a new chunk than to figure out the consistency of the existing chunk. So chunk segment storage is the component which we like to call SLTS, Simplified Long-Term Storage. The key point of this design is we are separating data from the metadata. The metadata about the chunk is stored in a separate table-based metadata store. Metadata is stored using a bookkeeper-based table. It's stored as key value pairs. The table is pinned to the container. The metadata updates are atomic, which means all the keys change at once or none at all. That simplifies the error handling in a major way. The metadata updates need to be efficient. They need to be infrequent. As far as possible, they need to be lazily writing data. They need to be cached extensively. So we are using a write-through cache for read performance. Like I explained before, the metadata records offer a point of extensibility. We can have access control list. We can have CRC-based checksums and whatnot. The requirement for metadata store are simple. They need to provide optimistic version-based concurrency. What that means is, in theory, we can use Zookeeper. We can use any key value store that provides version-based optimistic concurrency. The API that now we expect the individual storage provider to implement, it's vastly simplified. All the complexity of fencing is removed. It's concentrated in SLTS. It handles all the failure scenarios. It handles all the fencing logic. The API that we have for chunk storage is essentially a very simple CRUDL API, which you need to be able to create object, read object, open the object for read or write, delete the object, list the object. You get the attributes like size of the object. Optionally, you can merge two objects or truncate the object at the end, make it read-only. Again, the API is very simple. All the complexity is gone. So in short, I mean, I went through a lot of slides, talk about a lot of things, but what I want us to remember at the end is there is a certain reason why we wanted to do SLTS. There were certain problems we need to solve with SLTS. And here are the advantages of SLTS. From a technical point of view, we are clearly separating the responsibility. The storage providers must only support like just the simple CRUDL operations. The SLTS actually takes the responsibility of implementing single writer pattern, atomic appends, dealing with eventual consistency, dealing with creating creating segments out of immutable objects. Again, another advantage of SLTS is we are extensively using asynchronous programming model. And what that means is we have increased concurrency. We have higher degree of thread utilization, higher degree of parallelism, higher kind of read and write throughput, and also lower latency. One of the core reasons why we are doing SLTS is also robust failure handling. So all that is implemented by SLTS. The actual API that the storage providers have to implement is vastly simplified. From the functional point of view, the biggest advantage of SLTS is now we have a plugin model which enables third-party storage adapters to implement storage adapters for Pravega for wide varieties of systems. In near future, we will have a SDK and a test suite so that you can actually test your implementation against a given test suite. But one of the things is the batteries are included. Pravega does come with built-in adapters for NFS, HDFS, ECS, which has extended S3 storage. And in near future, we will have a S3 adapter for Pravega. It also uses its own built-in metadata store. So we already have Pravega table store, and we use it internally, and it's fine-tuned for SLTS usage pattern. So out of box with SLTS, you can start using NFS, you can start using HDFS, you can start using extended S3. In near future, you will also have S3. Again, it goes without saying that once we have the plugin model, there could be a community owned or community developed storage providers, for example, for Azure, for GCP, for Swift, and there are many other storage options available today, and we can create an ecosystem of storage providers. So let me conclude by giving a sneak preview of the roadmap. Again, this is tentative. We are not committing to any dates here. SLTS is experimental feature. Things might change. It's a new feature, so we might actually shuffle, what goes in what release. But here is a general timeline. We had an alpha release of SLTS in 0.8. 0.9 is where we are introducing SLTS. It's experimental. We have initial bindings for file system. We have for HDFS, for ECS. 9.1 is more like a service release where we are fixing stability issues. We are fixing other bugs. Next release, we are hoping that it's a stable release. And by stable, I mean the API is no more experimental. It's going to stay the same. It will be supported long term. The metadata written on the LTS will be supported. It will be backward compatible, forward compatible for the future. In next release, we will, like I said, the plan is to have S3 binding for AWS. We'll also have admin and diagnostic tools. We do plan to have a proper SLTS SDK and a test suite, and then we'll have some migration tools. In future, our goal is to make SLTS the Pravega default Pravega LTS subsystem. So that's a kind of a brief overview of what SLTS is. I think I am personally pretty excited about it, and I think it will be a good idea for you to take a look. And I'm looking forward to your feedback. Quick slide on how to enable SLTS today. So there is a config setting. You just kind of say Pravega service.storage.layout is equal to chunk storage, and that will actually enable SLTS. Please keep in mind that SLTS, because it changes the way data is laid out on the LTS, it's not backward compatible today. So it only works for freshly installed systems. But if you want to experiment, this is the setting you have to set. References, the design document is available on Pravega Wiki. It's a PDP 34 simplified tier 2. There is a Slack channel, Pravega LTS, in our Pravega Slack. So yeah, that's all I have for today. Please let me know what you think. I'm looking forward to your feedback, and definitely excited about SLTS.
Thank you, Sachin.
Thank you. So I will stop sharing, I guess.
Sure. We're quite a bit over time. I don't know if anyone has questions for Sachin. Diego would be next. He's implemented the SLTS interfaces for bookkeeper storage.
So Derek, I would like to suggest that we leave the remaining talks for the next session. I mean, we are way over time, and you know, I want to give proper time for everyone to present, and we are way over time. Need to be respectful of people's time.
Yeah, how does everybody feel about sticking around for Diego's piece? It goes along with SLTS, or should we just adjourn?
I will have to leave for one. I have a meeting right now. So before I leave, thanks everybody. Great set of talks. We need to do a bit better with respect to time management next time, but otherwise, I think the content was great. It was great to see everybody. I'm dropping off. Thanks.
Thank you. Thanks a lot.
Thank you.
Yeah. Rolo and Andre, are you guys okay to keep going, or what do you think about Flavio's suggestion?
But I don't know how, if anybody else is still willing to sit and listen to us.
Yeah, I'll stick around. I think it'll be good to have this stuff recorded. We can certainly reschedule if anybody wants to, but I'd definitely like to stick around for Diego's information at the very least.
Yep.
Yeah, but I'm at in 10 minutes I have to drop out too.
Okay.
So.
Well, maybe we wrap up with Diego and apologize for the going over time.
I take a really low time for the presentation. It's not any good. How was I seen the other one? Or for me, we can postpone to the next meeting if we are taking time locked.
Okay.
Well, no, I think let's have Diego's presentation, and we can also revisit it next time, so he can provide more information.
That'd be cool. Yeah, I think
initial implementation, then we can speak more about it. Then okay. Well, try to let you see a presentation if it's visible. I don't. You see something or non-idle?
Yeah.
No, I don't see anything.
Okay. Oh, I'm sorry. I'm terrible. Okay.
When I share screen, there's a couple tabs. There's like your entire screen or application window.
So. Well, I don't know if showing now.
Not yet.
Not.
Nah.
Oh. Okay, we'll try. Normally speaking, it was just 2 or 3 slides. Okay, Pravega normally needs some external support to store permanent data. We have seen the implementation for HDF, for NFS, but what can useful is to have the permanent data that are stored normally on such external tools directly in Bookkeeper. To achieve this, we can leverage on a tool that is Blobit, that we have already written for an email server to have a storage distributed, fault tolerant, replicated, and the tool is based on Bookkeeper, just to store the data and store his metadata on another tool that is RDB, that stores his metadata itself and the commit log on Bookkeeper. Blobit writes its data on one or more ledger and aggregate it on a local bucket to handle his this metadata. Then you can write named blobs on buckets, delete from buckets, append blob to it, and handle the deletion to Bookkeeper. So the metadata instead are stored on RDB, that is a database, a Java embeddable database. It's a share noting application that have sorry, it's my first presentation ever. Sorry. Such data work on table spaces that is a smaller replication chunk, okay, and they can fault tolerantly switch the table spaces on a different machine to achieve fault tolerances. Okay. Actually, the implementation itself for the SLTS is not too difficult, thank you to the simplified layer. Okay, actually, I work into the way to get all the configuration of Pravega about the Zookeeper and Bookkeeper, read them, use directed them to achieve a Blobit cluster and a RDB cluster directly into the JVM that runs Pravega. So.
Yeah, cool. That's and you have your plugin up on GitHub, is that right?
Yeah, I have a plugin on GitHub. Actually, is just a draft. Okay.
So using Pravega.
Sorry.
Is this using Pravega?
It's a plugin to for the SLTS. No, I didn't study your question. Sorry.
I was asking, is this using Pravega?
I think the right way to think about it is Blobit is an external storage that Pravega will use. And Diego's implementation actually implements the SLTS interface. So the
I see.
SLTS will be able to talk with Blobit, and we'll be able to store all the data in Pravega into Blobit.
I see. So which would store it in another bookkeeper cluster? Is that right?
No, the idea is to store on the same bookkeeper cluster.
I see. Okay.
Can configure for another one, actually.
It
idea
would
have something that you don't have to configure too much to achieve storage and the full tolerance for your data.
I think it does imply copying the data from bookkeeper to bookkeeper. You have to move the data, or maybe it's not. It's from. I'm wrong in saying that we have the data in the segment store cache, but basically I guess the segment stores would write the log to bookkeeper, and then it would write the chunks to Blobit in bookkeeper.
Okay. Okay. So this will eliminate the need for an additional long-term storage.
Yeah,
Right.
it's an additional one.
Okay,
So,
that's really interesting. It could be very useful.
Yeah,
I know internally
thanks.
to Dell we wanted LTS on bookkeeper.
And just like I in SLTS talk presentation I talked about is the aim is to open up Pravega LTS subsystems so that we can have more of these particular object stores or external storage systems that we can bind to, we can leverage, we can store data to. And that's the aim of SLTS. And I think Diego obviously has done a fantastic job of implementing this for SLTS.
So Diego, I had one question. Is there a limit on number of ledgers that we could have? Because I'm guessing for each chunk, you would be maintaining a separate ledger in bookkeeper, right? And with SLTS, the number of chunks could become order of magnitudes larger than number of segments. So where could we potentially start hitting the limits?
Technically, no, there's a hard limit. We don't create a new ledger for a new chunk, okay, or a new blob, blob in naming. So it's a blob that decide if write on the same ledger or split the ledger because it's too big, or split the blob in more ledgers because it's too big to host in one ledger. No, there isn't a hard limit on the number of ledger.
And what's your GitHub URL for this? Diego, what's your GitHub URL?
Question.
I'm sorry, what?
Probably I missed the question.
Oh yeah, what's your GitHub URL for the implementation of the SLTS interfaces?
Well, really, sorry, my English is really.
Oh, sure. Where can we find this on GitHub?
Okay, where you can find. Actually, we can get the path. Sorry, it's
It's on Enrico's. I may have found it.
Yeah, Enrico is unattended now. I get into sorry.
Well, I put it in chat. It's Pravega Blobit Chunk Manager.
Exactly. Pravega Blobit Chunk Manager. There are two stores, unfortunately. One has a typo with a double K. We had to
I
delete.
see.
That is the Enrico ones.
And then you have one?
Yeah. I'm getting hit. This is Pravega Blobit Chunk Manager with the 1K.
Oh, with 1K. Okay.
Exactly. Under the space is a space Diego Salvi.
Well, we can Google that, I guess, to find it. I see. Somewhere here it's linked to.
Excellent.
Oh, I see. Used by. There we go. Okay, so this is yours. This is the official one.
Exactly. That's the one.
We'll check that out. And I think you need our support to even run this, right? So we need to now provide you the hooks to turn on your external plugin.
Exactly. You need to attach it.
Yeah,
Sachin, that's on you.
There is a bug that needs to be fixed. Yes.
Okay.
We have
So,
a channel for this.
Diego, we'd like to probably have you back after you've been able to run this with our support. Hopefully Enrico can join you next time.
Yeah, hopefully.
Thank you.
Well, apologies about running over and I guess missing Andre's talk. Raul, or do you want to?
My slides, I posted my slides on the public channel. So on the public Slack, Pravega-KV-tables, I posted my slides if anybody wants to read them. And I can go over them next time, but I don't want to keep you guys waiting.
Yeah, that'd be great.
Yeah, we'll do the same.
Okay. Yeah, thanks, guys. Let me maybe just share this one kind of a closing slide. Thanks everybody for showing up, and we'll definitely see you next time. You can join us on Slack. There's some new blog posts. We haven't announced them, but check out blog.pravega.io for Raul's performance blog that he was going to get us up to speed on today, but we'll do that next time. The next meeting will be on the 16th about connectors, and we'll work in these couple updates we didn't get today, and certainly send me your feedback about today's meeting and what we should do for upcoming meetings. Thanks everybody for showing up and for putting up with the time constraints. So we'll improve on that in these future attempts.
Thanks a lot, Derek, for organizing this, and definitely excited to meet the community.
Yeah, you're welcome.
Yeah, this is great. Thank you.
The content was really incredible. I couldn't bring myself to interrupt anybody, so went over.
Okay, thank you.
All right, well,
Thank you.
Yep, see you everybody. Bye.
Thank you.
Thank you, Diego, for showing up.
Thank you.
Doing your part. It was awesome.